In this video, let's take a look at derivatives with respect to the chain rule, and I'll provide you a few examples. So what is this chain rule all about when you're coming across this maybe for the first time, or you're trying to understand a little bit better? I kind of like to do a visual for students, and the visual is the following. So we have kind of an input into a function, and that is not really anything special for us. Okay, so we're used to this particular item where we have some function and then we have some output. But what is different with the chain rule, it is for actual composite functions. So when you have an input which is fed into a function, okay, you'll have some kind of an output of that function. I mean, I called it u. And then that output is again fed into another function. So in this case, we have this right here. So this is my second function. And that is the composition really of two functions. Now you can continue this chain. Of course, you can have multiple functions even after where I have y. So you can have compositions of 3, 4, 5, and etc. So that might happen depending on what you are studying. Now, for calculus, when you're beginning, most of the time this is going to be related towards just kind of a chain of two. And it's called chain rule, and you'll see why in just a moment. So in order to construct this entire thing, what we would have is, if I was going along here, so I would have my x, okay, I would feed it into this function f. So what I would have is, as a result, my output would have been this. And then, I can say u is equal to fx. And then I take this u and then I feed it back into my new function, which I called g. It doesn't matter of the letters that you use. And then what we will have is we're going to have that our output y overall is equal to g, okay, with the new input u. And the way that we typically will write this, instead of writing it in this way where we kind of have almost like a substitution within there, we would write this in the following. So we would say g and then open bracket, and we're actually feeding the function fx. Okay, so it is an actual input into another function. So that's how we would like to write this. Now, another way that you're going to see this is that when you do have a composition of functions, instead of, utilizing brackets, what we sometimes will do is we're going to have that it is a composition of two functions. Okay, we do it kind of like this, where this right here is, saying that it's being fed back into this function, which is g, and then we designate the composition just with, a small little circle. Maybe I over exaggerated the circle. Typically it's a little small circle like this, and that's what we would have. And the reason why we actually use this particular circle instead of just using this, which definitely I like, especially when it's only for two, the reason is because you can have a composition of numerous, right, functions. So as I told you, this y could of course be also fed into another function, so maybe it's f, then it's g, maybe then it's h, and so on. And then writing them out like that, okay, if we wanted to use this notation, then it would have been annoying if there was another function down on the line here, because we would have to write this, okay, in the following way. So let's assume that this y, got fed into, so let's say we had another function here as an output. I don't know, maybe it was called h, right? And then we're feeding the y in here, and that's what we would have. So this would look like this. You would have h, and it would be fed into, so that this g gets fed into the h, but into the g, we had an f. And as you can see here, this becomes kind of annoying to try to see and then carry out the brackets. So instead, the math guys, okay, just simply write, okay, so this would have been h composed within from g, okay, and then composed from f, okay, and we know that, okay, the variable of the input was just x. And then we have this composition 1, 2, and 3, and of course you can continue this chain. Now, when you're first originally studying this in calculus, you're going to have just a composition of 2, but don't be afraid of carrying this forward into others as well, right? So that you can just carry it, moving forward into various compositions. So the main idea within here is that we want to be able to find out what this chain rule of the derivative is. So if I do have this right here, okay, so I'm going to just write it and pick it off. So if I have this, what is actually the derivative here? Now, we do have to make some assumptions. Now, as a student, you typically kind of omit these assumptions, and I'll be honest, I certainly had when I was studying this, but we can't forget that when we are working with derivatives and we have these functions, these functions have to be differentiable. So for instance, this f, should be differentiable, and then this g should also be differentiable. Okay, so that means that the derivative exists just for that function on its own without any compositions. So that is the assumption that we have. Now, if we have that assumption, then this particular derivative is actually not that hard to try to actually obtain. To prove it, that's a different story. I'm not going to do the proof here, so if you're interested in the proof, I've done the general proof for this. I'll put up a link up above there. It's for those who are kind of hardcore and want to be able to see it. Okay, so that proof is not very easy to try to understand, okay, and also to come up with. The more simpler proof is when our g is actually a power function. So when this g is actually a power function, then that proof is a little bit easier, especially if you understood the proofs for power functions. And if you want to see that proof, I'll put up a link up above there. Again, it's still for the hardcore, okay, students who want to know and understand. So you can take a peek there. But if you just want to know what the chain rule states, then we say that the chain rule in terms of the derivative, okay, is the following. So to obtain this, sure, you can go through the whole definition of the limit as h approaches to 0 and so on, but we don't want to do that, okay? So what we do is we take this function and we say that the derivative is the following. It is simply, okay, the fact of taking in the derivative of g, okay? So that's what this would be. So this would have been just the derivative of g, okay? And we do nothing to this input, okay, fx, and then we multiply it, okay, with the derivative of f, all right? And that is the chain. So the chain means, okay, that we have one chaining with another, okay? So it's the multiplication of the two derivatives, but the first one has the input f inside it. So what does this mean? Right? So like, what does this exactly mean? So let me just show you on one of the examples, and then I'll show you further examples afterwards. So for instance, if I would take this original right here, okay, so if I had something like this, let me copy this down. I'm going to bring it so just so you can see it on an example so that you can have some kind of a sense. And let's say, these are my particular functions, okay, that I would have. So within here, let's assume, okay, that my first function, okay, would have been something like this. Maybe it is, 2x plus 5, all right? So that is the first function. So what that would mean, that u is equal to 2x plus 5, okay? And now, let's say that my g, okay, within here, okay, is going to be, so I'm going to take my input, so that in this case it's my u, and my function is, let's say, nothing else, maybe this is going to be squared, all right? So this is something that we would have right here. Now, why is this a composition? Well, it is a composition because we have one function, we have an input which is fed into a function, okay, which provides us an output. So I call this output u in this case. And then that output is now fed into another function. So in this case, it's just being squared. And then we have an overall output. So the way that this would look like if we would write this all out as a whole, So, of course, y is just simply equal to u squared. And then the composition, because if I substitute this u back into here, then I get that my output is equal to, so my 2x plus 5, which is my u, and then I have this squared. So I have a composition really of two functions. Now, you yourself might say, well, wait a minute, but we studied, power functions. We know what the derivative of power functions are. Okay, if you've forgotten, I'll put up a link up above there for you with respect to power functions. And you might say, yeah, this seems like a composition, but can I not just simply say, hey, wait a minute, this is just squared. I know how to square this. Okay, so this is nothing else but 2x plus 5 multiplied by 2x plus 5. And I will obtain, so within this case, I would get 4. This is 4x. This would have been squared right here. Let's say plus 10x, okay, plus 10x plus 25. And overall, this expanded would have been 4x squared plus 20x plus 25. So you can say, well, I remember how to square these things. I did it in, grade 10. And from here you would say, well, I know what the derivative here is. This is just the application of the derivative for each individual term. So this is just using the summation rule for derivatives. And you would go ahead and you would say, okay, well, this is 8x plus 20, and then the derivative of that is just 0. So my overall derivative, okay, of my output would have been that. And you would have been correct, okay? And you would say, okay, that's fine. Now, this idea, of course, is correct. We didn't do anything wrong. The only problem here is, it's not always squared. What if this, instead of squared, what if we came across here and someone said, well, it's not really going to be square. Maybe it's going to be to the power of 7. And then that would mean that this had to be power of 7. And then you certainly wouldn't want to be doing this. Now, sure, you can use binomial expansion, from Pascal's triangle to be able to do that, where you can expand the whole thing out again and then take derivatives term by term. But that would take you quite a while. While here, this is much easier to do, because what the chain rule states is, chain rule just says, well, just take the derivative of g, assume that fx is just fixed, and then multiply it by the derivative of f and see what that gives you. So let's try that. Okay, so I'm going to take this, I'm going to duplicate it or copy it. Okay, now that is the actual derivative, right? So here is the application of the original chain rule. So now if I do this, now of course let me remove this 7. Okay, let's say that this was 2. And if I go back in here, so here's my g, right? This was squared. So what we're doing is we're supposed to take the derivative, right, of g, which was just the input squared. So u squared, right? So this just simply means, well, I know what the derivative of g is. Okay, so I'm going to write it here on the side. So if this was u squared, the derivative is just simply 2u. That's what the derivative is. Now, of course, u just means fx. So what we are doing here is we're taking the actual function itself, and this is going to be simply 2 multiplied by, okay, or fx is inside, which is going to be 2x plus 5. That's the derivative, and we're supposed to be multiplying this by the derivative of f. But but f itself was just 2x plus 5, so the derivative of that is just simply 2. So now, notice what happens. Well, 2 multiplied by 2 is 4, right? Bringing that 4 inside of the brackets in here is going to give us just 8x plus 20, which is exactly what we got over here. And it's much faster to be able to do that. I don't have to do the expansion. I can just go ahead and do the derivative. So in whole, okay, if we were taking this and we were trying to apply the chain rule, so let me just remove this entirely and then bring this back where our function is 2x plus 5. Okay, this is squared. So if I take the derivative of this, what it's saying is, okay, well, I can just do this. 2x plus 5. So what is the derivative of this, okay, where I'm keeping this bracket as is. And then I want this to be multiplied by the derivative of what's inside of that bracket, which is just 2. And again, that's going to yield for us this right here. So that's what the chain rule is. Let's take a look at a few examples. So hopefully this will make a little bit more sense to you and you can see it, how it can be applied. So I've prepared kind of 3 examples, okay, in here. And let's see how we would take this and apply the chain rule. So for instance, right here, now we're assuming that, of course, all of these are differentiable, okay, in this case, and they are. So within here, so this would have been my f, and then it's being fed into g, and g is just the power. So just as we did in the previous, I don't want to expand this. All I'm going to do is I'm going to say, all right, so the derivative is 3, bringing down the exponent, okay? I'm leaving, okay, that inside. Well, this is going to be 2, right? Because that is what the derivative of a power function is. And now I'm supposed to multiply this by the derivative of whatever is inside of the bracket. Well, the derivative of 4x plus 7 is just 4. So overall, this is simply 12, 4x plus 7 squared. And that is the overall derivative of this function f1, which is a composition of 2 functions, one inside of the bracket and the actual exponent. Okay, so that's the composition. How about this one? Right, so what if I would take this? So let me copy this. I'm going to bring it down right here and try to apply now the chain rule. So the chain rule is, well, I'm going to rewrite this first as 13x to the 5 minus 2x. This is going to be to the 1/2 because we have a radical. So what I have to do is, all right, well, I know what the actual derivative of a radical is. So that would come in front. So the derivative of f2 of x is equal to, so this would have been 1/2, 13x to the 5 minus 2x. I have to take or subtract 1, so this would have been negative 1/2 right here. And now I have to multiply it by the derivative of whatever was inside. Okay, so this is right here. So, well, the derivative of that, now it's not that pretty, but it would be 13, so times 5. So that is, so 13 times 5, I guess, is what, 65? So that's going to be 65x to the 4, and then the derivative of minus 2x is just minus 2. And now I have my entire derivative. Now it depends if your teachers want you to simplify this or not. If they want you to state where this is actually differentiable, then we do have to be careful because, please remember that for radicals, so this right here, okay, had to be greater than 0, okay, or 0 or greater than 0, right, in order for that function to be defined. So we're going to run into that problem again here. So this, of course, has to be, okay, set in a way that x, okay, is defined in such a way that, so this right here, because it's from the radical, so that would have to be 13x to the 5 minus 2x, has to be, okay, greater, okay, than 0. Now this is because it's now negative right here, so that means it would have been in the denominator. So we can't have it 0 because we would have it undefined. So right there, so that would have been our restriction, okay, on x. So anywhere aside from that, it is differentiable. okay? But that is the application of the actual chain rule that we have. Now, these, of course, get trickier and trickier, and then we can do all kinds of wonderful things that we can start. So let me copy this one. This is the last example right here, that we can start utilizing numerous rules for derivatives. Notice I have a subtraction. So what I will do is I'm going to use numerous rules. So I have one term. Now notice this term is a composition of two functions, one inside of the bracket and then the power. So from that, I can find out what the derivative of this is. So the derivative here would have been 4, 1 minus x squared, so this is 3, and then multiplied by, so this is going to be negative 2x, because that's the derivative of this right here. So that is my first derivative. That's the derivative of this. So that's all great. And now I have to find the derivative of this. So it's going to be minus, so that's the minus. And now I need the derivative of all of that. So I'm going to just shift this over, okay, right here, because this is not going to be the prettiest thing to be able to do. So just above here, I'm going to rewrite this. Notice this is a 5. This is, the square root. So we can write this as 2x squared plus 3x plus 1. And this is going to be 5 over 2. That is rewritten with a rational exponent. And now finding the derivative, this would have been 5 over 2. Okay, so times 2x squared plus 3x plus 1. 5 over 2 minus 1 is going to be 3 over 2. So that's that. And then multiplied by the derivative. Okay, so this is the composition. So multiplied by the derivative of this. And the derivative of that, okay, would have been, so the derivative of this is just simply 4x, okay, plus 3. So we would have been multiplying by 4x plus 3. So this derivative looks super complicated. And if you had to do this from first principles, where you're setting a limit as h approaches to 0, you do your difference, okay, of substituting x plus h, and then, subtracting, and then dividing by h, and then, trying to massage that to come up with all of this would have been a lot of pain. And it has been generalized that if you do notice the chain rule, then it just makes your life so much simpler. All right? So that is the application of the chain rule. Now, in here, it seems that everything is well behaved. We don't have any denominators, so we don't have to worry about any of that. We might have to worry about the radical a little bit, okay, in terms of is it defined or is it not defined. Okay, so we have to be careful with that one. But overall, finding the rule by the chain is super useful. So I have given you several examples and an introduction to this chain rule. And I hope that, you will now try and repeat the actual examples and see for yourself how do you find the derivative. All right. Thanks for watching. Happy studying, okay, in terms of calculus. Bye, everybody.